In this video, we will study about the basic physical principle on which the liquid penetrant testing works, and that basic physical principle is the capillary action. Before moving on to the technical discussion, let us first understand these basic terms: capillary action and surface tension. So capillary action is the phenomena due to which liquid such as water spontaneously rises up in thin tubes and fibers, and it rises because of the adhesive as well as the cohesive forces and because of surface tension. You can take the example of water which is present in a wide tube and in a narrow tube. So here these cartoons represents the water molecules. So here in wider tube you can see the cohesive forces, which is the force between the water molecules, is larger in comparison to the adhesive forces, because of which water is not able to rise up in wide tube. But here in thin tube, the cohesive force as well as the adhesive forces are you can say is in such a way that the water easily rises up in this tube, and adhesive forces are comparatively larger than the cohesive forces, because of which it easily creeps up in this thin tube. And the second one is the surface tension. So the cohesive forces between the molecules of liquid actually causes the phenomena of surface tension. So the basic definition which we study is the phenomena due to which the water behaves like a stretched membrane is known as surface tension. We can take the example of water which is there in glass. So if you see the top layer of the water that behaves like a stretched membrane, this is due to this cohesive forces between the water molecules. And if you see the water droplet, that water droplet actually forms a spherical shape, and this is also due to the phenomena of surface tension. Now if we have to see the capillary action from a more technical and mathematical perspective, then we can see this figure. So here in this figure, this is the water container, and in this water container a thin tube has been placed, and this figure shows a cut section view of this thin tube and this container. So in this thin tube a meniscus has been formed. So the if you take the example of a water in the glass, so the top layer actually which is formed of the water, we call it that meniscus also. So here you can see, if this is water, then due to this water a meniscus has been formed, and which is in a concave shape if you see from the top. So here this meniscus is formed due to the surface tension, and here T is the force, which is the surface tension force which is along the tangent to this meniscus, and this surface tension force forms an angle theta with this tube. And if we have to divide, or if we have to break down this surface tension force, we can break down it into cos theta and sin theta components. So cos theta component is the component which points in this topward direction. So here we can see this is the cos theta component which is pointing upwards. So here the rise and fall of this liquid in this thin tube depends on the downward force as well as the upward force. So whether the downward force is more or the upward force is more, because based on that the water will rise or fall in the this thin tube. So if first we will see the downward force. So downward force is just the force due to the weight of the liquid. So weight of the liquid we can express it as mg, and m we can express in the form of the density. So m is the multiplication of volume and rho, which is density, and volume of this is this cylindrical tube is 2 pi r square h. H is the distance from this top surface up to this meniscus level, and its volume is 2 pi r square h. And now we can easily write m, so which is the product of the volume 2 pi r square h and density rho. Then if you will take this first equation, so w is equal to mg. Now we know m and we know the value of g, so we can put the value of m 2 pi r square h rho and multiply it by g, and we can get the value of weight of the liquid. And now the upward force. So the upward force is the force which is due to the surface tension. So as the liquid rises upwards, so we have to choose the component of the surface tension which is pointing upwards. So here in this case is cos theta. The surface tension is the force per unit length, and if we have to calculate the total surface tension force, then we have to multiply the surface tension with the perimeter of meniscus. As it is the cut section view, if you will see the whole tube, so we have to multiply this t cos theta component with the perimeter of the meniscus. So here is t cos theta 2 pi r. So we have the downward force 2 pi r square h 0, and the upward force is t cos theta 2 pi r, where r is the radius of the capillary tube, h is the height of the tube, g is the acceleration due to gravity, density of liquid, t is the surface tension, and theta is the contact angle. So it is just the balance of the fd and fu based on which the water will rise or fall in the capillary tube. Now another concept is the wettability. So wettability is generally expressed with the help of contact angle. So here in this figure, different contact angles are shown. So here what has been done, that different materials are taken and we have dropped a drop of water on the surface of the material, and with the help of the high resolution camera we have measured the contact angle. So here you can see how we have measured the contact angle, and here this water droplet is completely spherical with a contact angle of 90.2 degree, whereas the contact angle decreases here, and here you can see this is the water droplet is a flat one, and here the contact angle, if it is 90 degree, it is known as hydrophobic, and if contact angle decreases, then the material moves towards the hydrophilic surface. So hydrophobic means the surfaces which repels water, and hydrophilic means which do not repel water, or the which attracts water or any liquid. So here, based on this contact angle, we can decide the rise or fall of the water in a capillary tube. So if you take the example of a lotus leaf, if you drop a water droplet on the lotus leaf, then that water droplet will simply roll down because of the super hydrophobic, or you can say the hydrophobic nature of that lotus leaf, and in that the contact angle is greater than 90 degree, which moves it towards the super hydrophobic nature. And here you can see this figure where the capillary tube is shown. So if this contact angle is less than 90 degree, means the water or this liquid has the hydrophilic nature, means it will try to wet this wall of the tube. And here you can see the concave meniscus, if you see from the top, and if theta is 90 degree, then here you can see the meniscus is flat here and it will not rise. And if theta is 90 degree, then theta greater than 90 degree generally leads to the hydrophobic nature, and due to this hydrophobic nature it will repel this walls of the tube, means it will not wet the walls of the tube. And here you can see the convex shape, and if you'll see from the top, you will see this convex shape, and it is known as the capillary depression. And if theta is less than 90 degree, this is known as the capillary rise. So here, due to the contact angle, the phenomenon of wettability occurs, and because of the contact angle and the wettability, capillary rise and depression occurs in thin tube. And capillary action is the phenomena due to which the penetrant seeps inside the crack. So here you can think of the paradox, that the phenomena which is responsible for the penetrant to go inside the crack is also responsible for its removal from the crack. So here you can understand it in this way, that when due to the capillary action penetrant goes inside the crack, then the excess penetrant which is there on the surface prevents the penetrant to come to the surface. But when you apply the developer, then due to the blotting action and due to the cohesive and adhesive forces and due to the capillary action, the penetrant again comes to the surface, due to which we get the indication of a crack or flaw. So this was all about the working principle. Thank you.